Hello everyone, let's continue with the General Chemistry 2 course, and today we're going to discuss the Wittig reaction. So let's jump into our app. Perfect. So I've been having some problems with my electronic pen. I hope that I just recently charged it, it will work well. Okay, so the Wittig reaction. We already discussed this in class, in online class, but we're going to make a review of it. And the overall reaction of the Wittig reaction is going to be this one. So you have a carbonyl group, mostly a ketone or an aldehyde, right? And what you do is that you will add the Wittig reagent, or also known as the ylide functional group. And what you will do is that you will transform this aldehyde or ketone into an sp2 compound, only made of carbons. Okay, so it will be something like this. And the Wittig reagent is going to have the next form. So it's going to be a phosphorus attached to 3 phenyls, right? And double bonded to a carbon, to an H, and to an R. So basically what we are doing is that we are inserting, right, this functional group and making a substitution for this oxygen. So we insert here into that through a reaction mechanism that we will see in a moment. And also I just want to make sure to understand that every time that I wrote something like this, I am, and it's attached to something, actually what I am saying is that what I have, sorry, let me erase, there we go. Okay, what I'm going to have is something like this. Also attach. Okay, sorry, the electronic pen is not working quite correctly again. Anyway, so this is like the overall reaction. Right now what we're going to do is that we will discuss with more time the reaction mechanism. So let's jump into it. So first of all, I have my phosphine, my triphenylphosphine, okay, attached to a phosphorus, and the phosphorus, remember, it's in the same family as nitrogen, so we expect that it will react as nitrogen. And first we need to create a nucleophilic attack, right, to the carbon that we want to attach to the carbonyl group, or to substitute by the carbonyl group. So first, let's say that I want to use this reactant, and after an SN2 reaction, right, what I will get is the Wittig reagent, or the ylide, or ylide, I don't know how to pronounce it, looking like this, right, plus the bromine. But the phosphorus, remember, is in the same family as whom? As nitrogen, so if the nitrogen loses these two lone pairs, this lone pair, sorry, is what's going to happen is that it now is going to gain a positive charge. So basically we need to do something with this positive charge in order to continue with the reaction. So what we're going to do is that now to my triphenylphosphine, right, attach to the hydrogens, right, I'm going to add a powerful base. So in this case I'm going to use butyl lithium. Okay, so it's a very powerful base. I have worked before with that, and it's pretty useful. So basically what we're going to have is the butyl, or butyl, in the negative charge, and is going to take away this hydrogen, because since this phosphorus actually is positive, is trying to pull the electrical density of this carbon, so it's making more available to an acid-base reaction this hydrogen that we have here. And what we're going to have is the triphenylphosphine attach with its positive charge, right, attach with a CH2 that has a lone pair, and it's going to be now a negative charge. So we have a positive charge, so a positive and a negative charge. So charges are balanced. We're doing something right. And remember that P phosphorus also have some d orbitals just because of the position that it has in the periodic table. So what is going to happen is that these two electrons are going to jump into the phosphorus and occupy a place in the d orbital, and what we will get finally is the ylide compound. Okay. Like this. And we can jump in between any of these structures depending on what we need, right? Of course, it's pretty clear that the ones that has the charges are the ones that are more reactive. So let's go and make our ylide interact with a carbonyl group. Very well. So let's say, for example, that I have a regular ketone, right? Something like this. And I need to make my Wittig reagent interact with it. So it's pretty obvious that the positive charge will go here, so it can get an interaction with the oxygen because it has a partially negative charge, right? And the phosphorus is going to be attached to a carbon that has two hydrogens, and this one has a negative charge. So it makes sense that it will interact with the partially negative. So what literally is going to happen is that these two electrons are going to jump and perform a nucleophilic attack to the carbon. But instead that the oxygen immediately try to keep the electrons, what is going to happen is that the electrons will jump towards the phosphorus to create a bond. Why? Because phosphorus loves oxygen. Okay, it's a very powerful bond, difficult to break, and since it is difficult to break, it means that it's easy to form. So what we will have is now the next intermediate. We're going to have the carbon now attached to the other carbon, so that is good because we like carbon-carbon bonds. The two substituents, the carbon attached to an oxygen, the oxygen attached to a phosphorus, right, and the phosphorus attached to the carbon. And don't forget that we have here our three phosphines. That's also pretty important. Very well. But guess what? One bond between oxygen and phosphorus is not enough. Phosphorus will want to have at least two bonds. So what's going to happen is that it's going to tell oxygen, hey, you know what? Release your bond with the carbon so we can have a double bond. And in exchange, I'm going to release the bond with this carbon so the other carbon doesn't loses the octet. And the oxygen is going to say, sure, why not? Sounds great. So what we're going to have, and I'm going to exaggerate bonds here just for you to see what is going on, is that now we're going to have this bond, the new bond that we created, with a CH2, okay? And on the other hand, what we're going to have, right, is this bond that we already have. Here it is, between oxygen and phosphorus, and the new bond that we have created, which is this one. So we will have also our three phosphines attached. Very well. So this is going to be our two products. Actually, these reactions work quite well. I've performed a few of them. The only problem is to clean these, right? The oxide of 3-phenylphosphine is difficult to clean, but on the other hand, I think it's a great reaction. So if what we do now is to correct a little bit more, right, the structure to a more plausible geometry, what we would have actually is this. And this would be the two products that I would have from the Wittig reaction. Now, the important thing here, right, is that, so for example, we use CH3Br, right, to insert this carbon where it, in the position of the oxygen, right? But you can be creative and basically insert anything that you need. So, for example, you can insert something like this. You can have a phenyl group attached to a CH2 and then attach to a bromine. So if we perform the Wittig reaction, what actually we're going to have, right, it would be something like this. We would be attaching, right, instead of a hydrogen, a phenyl group. So it's pretty cool because we can increase chains of carbons with double bonds, right, and with different functional groups according to whatever we need with our reaction. Okay, now let's discuss the other topic that we were able to talk about in class, and it's going to be name conjugate nucleophilic addition to alpha beta unsaturated aldehydes and ketones. Okay, very well. And we were discussing the possibility of having two different reactions, right? We can have the same molecule, right? The same alpha beta unsaturated, in this case ketone, right? With the interaction of a nucleophile. Very well. So as you can see, with this structure we have double bonds that are conjugated, and depending on in the nature of the nucleophile, we can have a nucleophilic reaction towards what? The carbonyl carbon, or an nucleophilic attack towards the beta position, right? Why? Well, because if we have an attack here, what we're going to get is that these ones will push these ones, and these ones will be pushed towards the oxygen, giving some sort of resonance, right? And hence, having resonance means that we have more stability. Very well. So, but how are we going to know if the nucleophile is going to attack either here or is going to attack either there? Well, it's going to depend basically on the conditions of the reaction, and we will have to see what we can do with that in a moment. Very well.